Good afternoon, Dr. Flynn. I'm going to be presenting my chemical synthesis project on the synthesis of 2,6-dimethylheptane, which I believe is compound 17 on the paper that you gave us. Okay, so 2,6-dimethylheptane is a saturated hydrocarbon, meaning that it only contains single bonds. The molecule belongs to the alkane family, and for this project, I focused mainly on the catalytic hydrogenation reactions. Specifically, I focused on reducing the alkynes to alkenes into the alkane, which is a single bond that you gave us, using the hydrogen and the platinum catalyst. Throughout the Chem 313 semester, we learned different functional groups and that can be transformed into other functional groups. My project mainly focused on converting the carbon-carbon multiple bonds into single bonds. The molecule can then be synthesized from either an alkene, which is, it is 2, to an alkyne intermediate, which is alkyne 3. Both pathways eventually produce the same final alkane, which is the compound you presented us with or gave us for our project. I apologize, I didn't have a whiteboard to work off of, so this is gonna have to be our setup. Okay, so what you gave us on the paper was this one. So this is going to be our parent chain right here, highlighted in the yellow. And that is going to be 7. 1, 2, 3, 4, 5, 6, 7, which becomes a heptane. Here we have two methyl groups at 2 and 6, which then becomes di, and then methyl, and then we bring down heptane. So for my project, I'm going to be showing that we use H2 and platinum as catalysts. We're going to do hydrogenation to get this into from an alkyne to an alkane, and then from an alkene to an alkane. Okay, so here we have our saturated hydrocarbon with 7 carbons in the main chain and the methyl groups on carbon 2 and 6. The alkanes like this are used, I believe, in my research. I could be completely wrong. Could be using components of fuel and can also be used as solvents. I found in the production of lubrications, I'm not too sure exactly what kind and what field they might be used in. Okay, so I'm going to make the first molecule, or my first synthesis of a catalytic hydrogenation, and we'll show the two pathways. One starts from the alkyne, and then the other one's going to start from the alkane. In both cases, the final product are going to be, again, this one right here, which is a 2,6-dimethylheptane. Okay, so for our first part, which I'm gonna put as A, this one's gonna be from an alkyne. And for me, I have to emphasize the YEN to make myself remember that that is a 3 or a triple bond. So here we are going to do, I'm kind of going to do this way. I hope this is correct, but this is how I was understanding it. And then here we have a CH3 groups, CH3, and then here we're going to have our catalyst, which would be H2 and PT. Here we are doing 1 dose. In my paper, I stated that we did the 1 dose. So we add the first amount of H2 with the platinum catalyst. The triple bond here is then reduced to a cis alkene, and then we use a second amount of H2 and PT towards the double bonds. So this one would break one bond, but we still have two bonds left, and it would reduce it to an alkane product. And this is when we get our good old alkane here. So there is a picture in the book, and it states, it's a chart where it shows it going from an alkyne, and the arrow points, and it goes to an alkane. Or we have it from an alkane to an alkene, and then from an alkene to an alkane. In this particular setup, here we would have used a Lindlar's catalyst, but the reason why I decided to go these two routes, here and here, is because the catalyst, instead of using regular platinum, the reaction would stop the cis alkene, and if we used sodium or liquid ammonia as stated in the book on the chart for this step right here, it would give me a trans alkene instead of alkane. Really quick, I'm going to draw, I kind of skipped a step, so we go from here to, and then we have the double bond here. So when this is added here and here, we then break the bond and we make a double bond here, which is then an alkene. Here we have an alkyne. So it's going to break. We're going to add another dose, as I stated in my paper, and from here we're going to go to a single bond, which is our final product. Okay, now, so we are going to do our part B, which is to an alkene, which I kind of explained, but we have to just go now from a double bond to a single bond, and the previous one was a triple bond to a single bond. No, I'm sorry, a triple bond to a double bond to a single bond. So here we are going to draw 1, 2, 3, 4, 5, 6, 7. Sorry, let me just double check that. 1, 2. Okay, maybe let's grab that one. Apologize. Okay, here we go. Again, CH3, CH3. It just helps me label them to understand this is my process. Here we add H2 and platinum, and then we're going to get, well, I actually drew it upside down here, so that's my fault. So here it's going to be upside down again, but in my head still the same thing. CH3. Okay, so here we have 2,6 dimethyl heptene 2 bonds to our 2,6 dimethyl heptane 1 bond. Okay, so we added our pathways here. We added our H2, which then we're going to, this way, come towards those double bonds, and our final product, here we get this. The general mechanism for the catalytic hydrogenation of the of the alkene. First, both H2 and the alkene stick to the platinum surface. Then the H bonds will break on the surface and the two hydrogen add to the same surface of the double bond. This is when we get the synthesis addition, and usually a cis alkene, which only gives one equivalent of H2. Platinum is then used because it lowers the activation energy and it makes the reaction happen faster. After the reaction is done, the platinum catalyst is removed from the mixture and the final product is the 2,6-dimethylheptane. This project helped me understand how different the reactions are that we used in class. I will admit I complained about having to do this project quite a bit to myself, but after doing it and sitting there and going through the book, it actually really helped me, and it showed me how to think through each step, what the reactions do, what the catalysts do, and how everything really has to be chosen to provide the correct conditions. So, in conclusion, the synthesis project showed how the catalytic hydrogenation can be used to convert alkynes to alkenes into alkanes. Both pathways were successful on my end. They produced the same final product, which is the one that you presented us with, which is the 2,6-dimethylheptane. The project really helped me better understand the reaction again, as I stated. It really just connected everything together rather than, I guess, memorization of individual reactions. I would say if I could get more of this practice, it would definitely help me. I understand after this project the importance of reagent choices and catalyst selections, and it just kind of gave me an overall understanding of, how OCHEM works. Now, I know that you wanted us to state something that OCHEM 313 helped us with, and let me just pull up my notes for that. Okay, so 2 remarks about Chem 313 made me really realize how much of a foreign language this class is. I know that I had multiple warnings about it saying it's a completely different thing that you really have to, either you understand it or you don't, and I definitely struggle in it. I spent many hours reading the book, going over things, and I still think I don't get it, but I'm proud of where I am. I will say that 2 things that I learned during this semester is the importance of Gen Chem. I did great in Gen Chem 1. Barely got there in Gen Chem 2, but I see how much everything travels over and how much everything transitions over. And if you don't have the fundamental understandings, you're really gonna struggle in OCHEM. So I'm really trying to brush up on all of that. I am definitely learning that failing is okay. This class has really taught me that. There's been times where I have been given a quiz or an exam by you and I am looking at it and I'm just kind of blank. And I have to remind myself to, retrace back into my general knowledge of things and really see what I can pull out. And that has been really helpful for me. I will say I really liked naming. I think IUPAC was my favorite. It was a little bit challenging. Definitely took me a while to get where I needed to get. But I think that was definitely one of my favorite parts. Now I can look at things as simple as my home products. And as a matter of fact, I have one right here. The other day I was looking at cooking spray and I noticed that it has dimethyl silicone and I'm like, whoa, I know what that is and I understand it. And it's crazy how everyday life things come into play and how, just reading things, it's like, whoa, that clicked. I can picture it in my head, or I can sit there and I can sketch it out and I can understand what that looks like. And I really enjoy this aspect of the class. I enjoy, finding everyday things around me and I'm like, I can picture that in its form. Or, well, that one looks complicated. Let's try and sit down and figure that one out. So again, while this class was hard, it was definitely fun, challenging, and I appreciate everything, and I appreciate all your time that you gave us, and I wish you the best from here on out. I hope I pass this class, but if not, I also understand. That's a reflection of me as a student, and you know, not in a bad way. I understand that sometimes, we have to go back and retrace our steps, and that's how we get better. So, thank you.